We will discuss permanent magnet brushless motor drive. The key feature of this permanent magnet brushless motor drive is high power density and high efficiency attributed to the use of high energy permanent magnet material. The permanent magnet brushless motor drive have shortcomings such as high cost and thermal instability of the permanent magnet material. But they are becoming dominant in the market share of electric vehicle motor drives. Permanent magnet materials are the key of permanent magnet brushless motor drives that provide the machines with lifelong excitation. So, in overview, they have high efficiency and they have high energy permanent magnet material are the major parts, but shortcoming is because of the cost and thermal instability. The major types of permanent magnet material which are widely used for electric drives. We'll discuss these materials. The first material is the ferrite material. Ferrite magnet was earlier invented in 1930s. It has been widely used as commercial magnets for the last few decades because of the abundance of raw materials and low production cost. The advantage of ferrite material are high electrical resistance, which can suppress the corresponding eddy current losses. And the drawback of ferrite material is high temperature coefficient and low energy density, leading to sensitive to temperature variations and bulky in size for applications to permanent magnet machines. The second permanent magnet material is alnico, that is, it is iron-based aluminum nickel cobalt alloy, which was invented in 1940. The advantage of alnico is it was the first modern permanent magnet material offering high resonance. Because of its high Curie temperature, it can be used at high operating temperatures. The drawback is its coercivity is low so that it is very easy to be demagnetized. So it is the property that retains the magnetivity and it can be demagnetized, which limits the corresponding application to permanent magnet machines as it can lose the magnetism. The third is samarium cobalt SMCO. Merits are high remanence, high coercivity, high energy density, high Curie temperature and low temperature coefficient. It is well suited for the application to permanent magnet machines which desire high power density, high efficiency and high stability. The demerits of this material is cost is the key drawback. Particularly rare earth element, samarium is very expensive. The next magnetic material is neodymium iron boron, NdFeB. The first produced in 1984. This is the rare earth permanent magnet material which has better magnetic properties than samarium cobalt material. The merits of neodymium are it is relatively less expensive rare earth element. The corresponding cost becomes reasonable for applications to PM machines. Demerits of NdFeB are the relatively low Curie temperature is the major concern, which limits its use for high temperature applications. This is the graph that shows the deployment of permanent magnet materials. You can see this is the BH maximum versus the year. We can see the ferrite material which started in 1930, then alnico from 1940 to 50, and they are still changing. But if you see the samarium cobalt has gradually increased BH value, that is kilojoules per meter cube, and NDFM, which is invented later, and it is at the you can say the highest BH value. A reminance BR denotes the strength of the magnetic field produced and the coercivity. HC denotes the resistance to becoming demagnetized. So here you can see HC BR graph. The maximum product of an operating point on the characteristics is dubbed as the energy product, that is the BH, which actually represent the corresponding energy density of the material here. PM properties, permanent magnet properties are usually temperature dependent and vary according to the temperature coefficient. Exposure to temperature, called the Curie temperature, the permanent magnet material completely loses its magnetization. System configuration of permanent magnet brushless motor drives. The figure shows the system configuration of permanent magnet brushless motor drive. The PM brushless machine is designed with sinusoidal distribution of air gap flux and distributed arrangement for stator windings. The machine operates as synchronous machine, so called permanent magnet synchronous machine or PM brushless AC, that is BLAC machine. Similar to induction motor drive, permanent magnet synchronous motor drive adopts sophisticated speed control strategies like field-oriented control and direct torque control, which generally demand an expensive position sensor such as the absolute position encoder or resolver. Although this position sensor can be ignored theoretically for open loop operation, this strategy is seldom adopted for EV propulsion. So sensors has to be used. So here you can see the diagram, the permanent magnet brushless machine with voltage fed inverter. This is the source, battery source. Current and voltage are sensed. Also position is given to the sensors and the sensor will give the input to the electronic controller with desired command, and it will control the voltage fed inverter and input to the PM brushless machine. When the PM brushless machine is designed with trapezoidal distribution of air gap flux and concentrated arrangement of stator winding, the machine operates like DC machine but without brushes, so called as permanent magnet BLDC machine. So the important thing to be noted is when machine is designed with trapezoidal distribution of air gap flux. So air gap flux is trapezoidal in nature and windings are concentrated stator windings. So it is the permanent magnet BLDC. The corresponding speed control is relatively simple, in which the stator currents are controlled in such a way that rectangular current properly aligns with trapezoidal flux. So the currents are rectangular in nature and the flux is in trapezoidal distribution. The position sensor is mandatory to ensure the synchronization of the current with the flux. The resolution requirement of this position sensor is not demanding since only 6 commutation instants are needed per electrical cycle. In general, low-cost Hall position sensor is adopted. Major advantages of permanent magnet brushless machines. Since the magnetic field is excited by high energy permanent magnets, the overall weight and volume can be significantly reduced for a given output power, leading to higher power density. Because of the absence of rotor copper loss, they inherently offer high efficiency. Since the heat mainly arises in the stator, it can be more efficiently dissipated to the surroundings, leading to easier cooling. As the permanent magnet excitation has no risk of manufacturing defects, overheating or mechanical damage is uh, not there. They inherently offer high reliability. Because of absence of copper winding in the rotor, they possess lower electromechanical time constant and hence better dynamic response. The permanent magnet will offer these benefits. It is the robust construction and it has the good response, dynamic response. Disadvantages of permanent magnet brushless machine. Since the high energy permanent magnets are based on rare earth elements, the machine cost is higher than that of the induction counterpart or its opponent. As the permanent magnets are located in the rotor, the mechanical integrity of the rotor, especially the surface mounted permanent magnet, has a problem at high speed operation. Because of the inherently uncontrolled permanent magnet flux, the constant power operation range is also limited. In case the machine is not properly designed or operated, the permanent magnets may be accidentally demagnetized by a high armature reaction field or under high operating temperature. So the armature reaction, that is the effect of magnetic field produced by the armature conductor on the main field or the operating temperature, can demagnetize the magnets. The family of permanent magnet brushless machines has two members or two types: permanent magnet synchronous machine and permanent magnet BLDC machine. The permanent magnet synchronous machine has been widely used for electric vehicle propulsion. Meanwhile, the permanent magnet BLDC machine is becoming more attractive. The structure of permanent magnet brushless machines. Figure shows the structure of permanent magnet brushless machine. It mainly consists of stator. Here we can see the stator. It is the stator and this is stator frame. This is stator winding. This is the rotor on which the permanent magnets are placed. This is the red color is one permanent magnet, then blue color another permanent magnet, then lower red another permanent magnet, and this side blue. So these are the permanent magnets placed on the rotor. Now this is the bearing and shaft. Compared with the induction machine, it is relatively simpler because of the absence of cage bars and end rings. So no conductors on the rotor or cage like induction motor. Since the associated heat losses in the rotor is not significant, it generally does not require to mount fan blades on the rotor or shaft for forced air cooling. We can see the stator and this coils, and these are the permanent magnets on the rotor. N, this is 1, and S, and this is the corresponding stator and the stator winding and the conductors. So you can see the axis between these two magnets is the quadrature axis, and along the magnet it is the direct axis. The principle of permanent magnet brushless machines. The permanent magnet synchronous machine operation can be discussed with these equations. The permanent magnet synchronous machine has balanced three-phase sinusoidal distribution of air gap flux and sinusoidal distribution of armature winding. The three-phase induced EMF waveform can be expressed as phase A, EA, phase B, EB, and phase C, EC is equal to the sinusoidal waveform equation EM sine into omega t. Then phase B EMF will be Em sin omega t minus 120 phase difference. And third one, EC is equal to the Em, that is the maximum value of the induced voltage into the sine of omega t minus 240, that is it is lagging by 240. So this is the three-phase distribution of the air gap flux. Now Em is the magnitude of back waveform, and omega is the angular frequency, as we know. For proper operation, the machine is fed by balanced three-phase sinusoidal currents as given by the equation. To get this EMF, the current fed is the sinusoidal. So for phase A, IA current, for phase B current IB, and phase C IC, and the magnitude of currents are given like this, and it is sine omega t minus phi, that is it will lag with a phase difference to the corresponding voltage equations or back EMF equations. So phi is the phase difference between the current and the back EMF. The converted electrical power can be calculated by calculating PE, power is equal to product of instantaneous is EMF into the current. So EA into IA for phase A plus EB into IB for phase B plus EC into IC phase C. If you put these equations, corresponding equations, that is EA, EB and EC equations with these sinusoidal forms, and IA, IB, IC into this form of equation with sign values, then after simplification, that is sin into cos, and get the solve, we can get 3 Em Im by 2 into cos phi. Thus, the developed torque of this permanent magnet synchronous machine can be obtained, that is torque is equal to electrical power divided by this omega. So we can get this 3 Em Im divided by 2 omega r into cos phi, because we can convert this by simplifying this equation. So which is a constant at a given speed omega r. So developed torque can be maximized by controlling the phase difference between the armature current and back EMF waveform to be 0. So phase difference has to be 0, then you can get this value as the maximum, as cos 0 will be 1 here. Here we can see the waveform power production of permanent magnet synchronous machines. This is EA and this is IA. So power is equal to EA into IA. So you can get this power. Power is equal to EB into IB for B phase. We can calculate this. And PC is equal to power of the C phase equal to voltage into current EC into IC. So instantaneous power, we can calculate PA plus PB plus PC is equal to 3 by 2 EM IM into cos phi. Now we can get the permanent magnet brushless DC machine operation. So the earlier was the permanent magnet synchronous machine operation with the sinusoidal input, sinusoidal distribution of the air gap flux, and sinusoidal distribution of armature winding. Now we are discussing permanent magnet brushless DC machine operation. The permanent magnet BLDC machine adopts the concentrated armature winding in the stator with 120-degree coil span. As the permanent magnets in the rotor cover 120-degree pole arc, the three-phase induced back EMF waveform are trapezoidal with 120-degree flat top region. So this is the important thing here. So the back EMF waveforms are trapezoidal with 120-degree flat top region. So here we can see the EMF waveform, which is the trapezoidal one. And here we can see the current waveform, which are the rectangular in nature, i.e. For proper operation, the machine is generally fed by balanced three-phase rectangular currents, as shown here, rectangular currents, with 120-degree conduction periods, here you can see, which coincide with the flat top regions of the back EMF. Each phase power is simply equal to EM/IM over the conduction period of 120 degree and 0 over the non-conduction period of 60 degree. At each instant, one phase power is equal to 0. So there will be conduction period 120 degree and 0 over non-conduction period of 60 degree. So here we can see this EA into IA, then EB into I, then EC into IC. Because of this, the resultant will be having this conduction period and then 0 and then again conduction. If you add this total power, PE is equal to PA plus PB plus PC, it will be 2 EM into IM. Now, while other two phases are EM, IM, the converted electrical power is simply summation of all phase powers, which is 2 EM into IM. Thus, the developed torque of BLDC machine now can be expressed as torque is equal to power divided by omega R. So 2 EM IM divided by omega R, which is constant at given speed omega R. Differing from the PM synchronous machine, if we compare with this, PM BLDC machine produces maximum torque naturally. So here we are getting this maximum torque. On the basis of the same current rating of the power devices for the two types of permanent magnet brushless machines, their current amplitudes are both equal to the current rating IP. Hence, the ratio of their power outputs, PM BLDC power to synchronous power, we can obtain from the earlier equations, and taking the ratio we can get this 1.33 divided by cos phi, so which indicates that PM BLDC machine can offer 33% higher power capability than permanent magnet synchronous machine. So ratio from this PM BLDC power to PM synchronous power is 1.33, so we can get 33% higher power capability by using PM BLDC machine.